Okay, so I want to talk about how to find a Jordan basis. Now, this is something that's a little bit beyond what we're going to cover this term in the course itself. So this is not required knowledge, but I do think that this is good. A little bit of mathematical weightlifting. It's good exercise if you're looking for a challenge on your understanding of the ideas. This would be good practice in thinking about a lot of the stuff that we've been doing. How do you find a Jordan basis? The short answer is that it's a very hard problem in general. But there are some nice special cases that are very useful and not that hard to do. That's what we're going to talk about. Okay, so recall that if you know a Jordan basis, there's a lot of great things we can do. If you know the Jordan basis, you can write down that change of basis matrix. You can conjugate to get the Jordan form. The Jordan form will allow you to do matrix exponentials, which allows you to solve differential equations. All of this comes out of having a Jordan basis. How do you find it? Okay, let's start with some special cases. The first special case is a kind of a freebie, and that is if you have a diagonalizable matrix. Well, if it's diagonalizable, the diagonal form itself is a Jordan form. And so the eigenvectors, your complete list of the n eigenvectors that you use to diagonalize, those eigenvectors are a Jordan basis. So nice, easy one to get started. Okay, harder one. What if your Jordan form looks like this? And now don't forget what we mean by Jordan form is the linear transformation that your original matrix A is representing in the first place, viewed with respect to this new basis, what I call the Jordan basis, because it puts the matrix into Jordan form. Okay, so what can we do in that case? Well, so I'll make the observation that we can then take our linear transformation. We can subtract lambda times the identity and ask, what does that look like with respect to our Jordan basis, which we don't know what it is yet, right? But we know it exists. And so what would this look like? Well, T with respect to that basis is this, right? And from that, we are then going to subtract lambda times the identity. And of course, lambda times the identity always looks the same with respect to any basis. That's an easy little practice problem you can confirm for yourself. So what this does is this just subtracts lambda along the diagonal, thus giving us these zeros. So nice punchline. This is how you represent T minus lambda I with respect to the script V basis, and then you can interpret accordingly. I'll zoom out so I can fit this all on. You can interpret accordingly, and you get these facts relating vectors in the Jordan basis. Okay, now let me just remind you where these come from. The rule for what it means to represent a linear transformation with respect to bases are you take your input basis vectors, right? The Jordan basis that we're talking about. You do the linear transformation to them. Now we're doing everything with respect to the standard basis here. So with respect to the standard basis, T minus lambda I is A minus lambda I. And then the results are written as columns that you interpret. Well, let's see, I'll do it like this. Columns that you interpret as telling you those images with respect to that basis. And so you get here 0, V1. Ooh, that didn't work out the way I wanted it. V1 and V2. Okay. All right. Now, this is not news. We have seen these equations before. You may recall we wrote down something pretty similar to these equations in the notes when we were talking about matrix exponentials and evaluating matrix exponentials on Jordan basis vectors. We wrote down pretty much this. I just kind of like this alternative point of view to get to it, where we think of this A minus lambda I, we think of this minus lambda I as effectively crossing out the corresponding diagonal entries. I just kind of like that. Okay. Okay, so what does this tell us about how to find a Jordan basis? Well, in fact, this is how you find a Jordan basis. You can solve that for V1. I missed. You can solve this for V1. And once you know V1, well, then you can solve that for V2. And once you know V2, then you can solve that for V3. And now you know V1, V2, V3, and of course, those are your Jordan basis vectors that we were interested in the first place. Okay, so it's really not that big of a deal in this case. Now, of course, I was looking at a very special case of this specific Jordan form, assuming that this is the Jordan form. So that being the case, there's a little algorithm and it will find your Jordan basis for you. Okay. All right, now there's a couple little mechanical details in practice. How do you actually do this and how do you keep your life simple? There's a temptation to look at this and say, oh my gosh, that's 3 separate row reductions. After all, there are 3 systems there. So am I gonna have to row reduce 3 times? Well, let me remind you from chapter 1, when you have 3 systems that all involve the same matrix of coefficients, which we have here, right? All 3 of these matrices are the same. Then you have a nice little trick you can do. You can take your matrix, put it next to the identity, row reduce, and in the process of reducing your matrix, your coefficient matrix down to its reduced echelon form, you will simultaneously be producing the E matrix that executes that row reduction. So a real neat trick from chapter 1. Anyway, that being said, you are effectively row reducing all of these systems all at the same time. So these systems here, by using the R and the E that you know you're going to end up with, right? Then we know that these blue equations are equivalent to these purple equations that are already row reduced. So you really only have to do just the 1 row reduction. You're going to do just the 1 row reduction, and that will apply then to all 3, in this case, 3 of the equations you need to solve. Okay. All right. Now, again, that was just a special case. By the way, you can look at my old exam questions, so my old exam questions, the ones in the announcement that I made that you're not responsible for. I did this trick in those solutions. So you want to see some numbers. Okay. Again, though, this was just one special case, right? That's if your Jordan form looks like this, specifically. What if it's more complicated? Reasonable question, right? So what if, for example, what if your Jordan form looks like this? Now notice here I have an eigenvalue block, and then I have here another eigenvalue block with a different, well, of course, a different eigenvalue. Can it still do the same thing? How's this different? And it's not that different, really, as it turns out. So the point is, now you are going to have to actually do a couple of different deal with a couple of different transformations and a couple of different matrices. But notice that if I look at T minus AI, and again, write it with respect to this basis, you're subtracting A's along the diagonal. And it just happens to be that subtracting A's on the diagonal along in there turns those numbers into zeros. Now, it turns these numbers over here into a bunch of junk that, I mean, it's B minus A, but it's something that we don't actually care about. Not 0 is the point, right? So I could have written B minus A. I just wrote little scratch marks because, well, we don't care. Okay. And then likewise over here, now you can also look at T minus BI. Again, you're going to be now subtracting along the diagonal, this time subtracting B. And so you get those turn into zeros. very nicely. But these turn into not 0, and beyond that, I don't care. Okay. All right. So what do you do with these bits of information? Well, you look at the appropriate columns, and this is, in fact, all we need to solve for our bases. So in particular, this equation tells me this. This equation tells me this. I can solve the light blue equation for V1. Once I know V1, I can solve the dark blue equation for V2. Yeah. This equation tells me that, and likewise, this tells me that, and this tells me that. So I can solve the yellow equation for V3, and then the orange equation for V4, and then the red equation for V5. So one at a time, one eigenvalue at a time. But you do have to look at the two different matrices in order to get the equations that you need. But we do have together then sort of dealing with one, you might say, one eigenvalue block at a time. We have equations that will allow us to solve for our Jordan basis. So there's sort of parallel calculations you have to do, right? I mean, you have to look at this part and solve these equations to get the first two vectors. And then you have to look at this part and solve these equations to get the second, well, to get the last three Jordan basis vectors. But really morally the same idea as what we did on the previous page. Okay. All right. So, I mean, is this it? Is it just always going to be kind of like this? And we have a method, and this always works, and there's no problems. Wouldn't that be nice? Sadly, it's not the case. Sadly, it does get weirder. And so this one actually looks easier. This is only 3 by 3 in particular. And it's tempting to say, hey, there's only one eigenvalue, right? Just that A, I'm only going to be looking at the one. I just need to look at T minus AI. All the diagonals disappear. I get some bunch of easy equations to write down, right? You get these equations. What's the problem, right? Find an eigenvector. Well, you're going to find two eigenvectors. You can see these columns here. There's two eigenvectors. There's two diagonal columns, and therefore we're going to have two eigenvectors. Should be easy. And then you only have one extra equation to solve, right? This one leads you to this equation. So shouldn't you be able to do that? Here's the problem. And I'll start off with an understatement of the problem. Between these two eigenvectors that we found, how do I know which one is the one that goes here? Right? Is it V1 or V? I mean, I can say, well, it's the way I have this set up, it's V1. But when I find two eigenvectors, which one's V1? Which one's V3? They just appear to be eigenvectors, right? I've got two. Which one do I want? And that is an understatement of the problem. It is actually significantly worse than that, because really, when you find two eigenvectors, remember, that's just kind of sloppy language for what we've actually found. When you find two eigenvectors, you have found a basis for a two-dimensional vector space of eigenvectors. How do I know for sure that these two that I've found, that one of them will necessarily be this one special V1 eigenvector? And I claim that V1 is special. There is something very special about V1. Specifically, notice V1, you can see from this equation right here, V1 has to be in the image of that matrix. You can see what the image of this matrix is. This matrix only has a one-dimensional image, right? This matrix has a one-dimensional, there's only one non-zero vector that comes out. So I'm looking not just for any old eigenvector, but I am looking for an eigenvector that is on this, this special line here that is the image of a minus little ai. And when you just solve and you find your two eigenvectors and whatever happens to come up, and you found your these two, it's not just a question of which one of them is right. In fact, it's probably the case that both of them are wrong, right? Probably neither one of them is actually on the image as they are supposed to be, right? And so the challenge then is to find that special eigenvector that both is an eigenvector and is also on that image line. Now, this is not that big of a, this can be done. It's just that we're getting further into weeds, and this case is not the only case of this level of annoyance that we have to deal with. This is just sort of tip of the iceberg of how complicated and annoying this process can be. So what I want to say here is this case is hard. Right. And I don't want to talk through sort of, the more I go in this direction of, how do we deal with these kind of hard cases, then the more we have to kind of keep going. And it's actually, it's a hard problem. So I'm going to ignore where to go from here, but I do want to make the nice observation, though, that there is a very good safe case that's useful in a lot of circumstances. And I'm going to explain why it is that this one's safe. If every eigenvalue has exactly one eigenvector, we're good. And our previous method works fine. And there's no issues with having to worry about whether you've got the right eigenvector or, is this in the image, and what is there going to be? Am I going to be able to solve these equations? What if I get a counter? Nothing like that will happen. You are safe if you stick to this special case where every eigenvalue has exactly one eigenvector. And of course, now we know furthermore, by the way, that this is something that will present itself pretty quickly. We know how to find eigenvalues. It's very straightforward. Once you have those eigenvalues, it's also pretty straightforward to find the eigenvectors, and you can then just explicitly look. You don't have to know what the Jordan form looks like. You can just count eigenvectors. And if you have exactly one for each eigenvalue, I claim we're good. And to see why, let's go back up to here. This is such a case. Let's see here. This Jordan form here, right? We have two eigenvalue blocks. There's the first one, eigenvalue A. One diagonal column, one eigenvector. One basic Jordan block in that eigenvalue block, you might say, therefore one eigenvector. And then likewise, here's another eigenvalue block in which there is, well, one diagonal column and therefore one eigenvector. Again, said differently, there's exactly one basic Jordan block inside that eigenvalue block, just like over here, there's exactly one basic Jordan block inside of that eigenvalue block. So I claim we're good. And I'm going to use this specific example here as a model for arguing why it is that this case works fine. And let's just look at this side over here. We'll look at this eigenvalue block, which leads to these equations. How do I know this is going to work? How do I know that I'm not going to have a problem like we had on the next page? Well, a couple of observations. I know that there is a Jordan basis. It definitely exists, right? There's definitely one out there. There's only one eigenvector. Okay, keep in mind, now that's sloppy terminology. When I say there's only one eigenvector, what I really mean is there is a one-dimensional eigenspace, right? I will find, it would feel, one eigenvector. But what I mean by that really is that there is a one-dimensional eigenspace. Okay. Well, again, I know there's a Jordan basis. That means that I know that there is a V3 that works. Let's suppose that V3, the one that works is this. And let's suppose that I don't find that vector. Well, suppose I find, this light blue vector, it's got to be a scalar multiple of that. And so punchline then, if you find what you might be tempted to call the wrong eigenvector, if you choose here, let me circle that a little bit better. If you choose a scalar multiple of the right eigenvector, again, we know that a Jordan basis exists. We know there is a right eigenvector, and there is at least one eigenvector that will work. Right? If you pick a multiple of that, okay, well, then fine. You picked a multiple of that, okay, well, then you'll just get a multiple of the next vector as well. And then over here, you will just get a multiple of that next correct vector. So you'll just get a fully scaled alternative, just as good Jordan basis. So in some sense, there's nothing that can go wrong. Another way to say this is that because there is only a one-dimensional eigenspace, right? Because there is a one-dimensional eigenspace, the eigenvector that you're picking just can't be in the wrong direction. There's not enough directions in a one-dimensional eigenspace to pick a wrong one, and scaling is just not a problem. Okay. So nice tool then, and this actually gets back to at the very start, nearly the very start of this talk, and I made the observation, sort of the confession of do I have to know what the Jordan form looks like before I start doing this process? Not really. All you need to know is that every eigenvalue has exactly one eigenvector, and that will guarantee that your Jordan form is such that this process will work. Give you your Jordan basis and you're done. Okay, so I think this is a really interesting discussion. Again, I'm not going to give you the full method for how to find a Jordan basis in the general case. It's a little too much, but I think there's some really nice ideas in this discussion, and I think it's a handy tool to have in your toolbox to know how in a fairly reasonable collection of cases, such as these kinds of Jordan forms, that you know how to find a Jordan basis. Okay, hope this has been useful.